Welcome to Project Management. In this video, I will talk about how to develop a project network. A project network is a diagram that graphically describes the logic sequences, interdependencies, and start and finish times of the project activities. The network is developed from the information collected from the work breakdown structure. It provides the basis for scheduling labor and equipment. It can be used to enhance communication among project participants, provides an estimate of the project's duration, and provides a basis for budgeting cash flow. A project network is a tool that highlights critical activities that should not be delayed. There are two different ways to representing a project network: activity on node network and activity on arrow network, or AON and AOA. An AON network uses a node to depict an activity, and an AOA network uses an arrow to depict an activity. The activity on node method has come to dominate most projects, and we will only introduce this method. In an activity on node project network, an activity can include one or more work packages. The node depicts an activity, and the arrow shows dependency and project flow. It's good practice to have the same people who developed the work breakdown structure to develop the project network to guarantee the consistency and continuity. Let's see some terms used in developing project networks. An activity is an element of the project that requires time, either work or weight, but may or may not require resources. Activities that consume resources are easy to understand. Examples of activities that do not require resources include waiting for contracts to be signed, materials to arrive, drug approval by the government, budget clearance, etc. The diagram on the right is a part of a project network. It has 4 activities: A, B, C, and D. There are 3 basic relationships among activities: predecessors, successors, and concurrent. A is C's predecessor. B is also C's predecessor. C is A and B's successor. A and B are concurrent or parallel activities. C and D are also concurrent activities. A merge activity is an activity that has 2 or more immediate predecessors. That means more than one dependency arrow flowing into it. In this example, C is a merge activity. A burst activity is an activity that has more than one immediate successor. That means more than one dependency arrow flowing from it. In this example, B is a burst activity. A path is a sequence of connected and dependent activities. For example, ABC is a path. BCE is a path. ADE is a path. A critical path is the longest path through the activity network from the beginning to the end that allows for the completion of all project-related activities. The critical path marks the shortest expected time in which the entire project can be completed. Delays on non-critical paths may not delay the entire project, but delays on the critical path will definitely delay completion of the entire project. In this diagram, the numbers above or below the activities are their durations. Activity A takes 2 days to complete, B takes 3 days, and so on. We have 2 paths from the beginning node A to the end node E, ABCE and ADE. The total length of ABCE is 2 plus 3 plus 1 plus 4. It's 10 days. The total length of ADE is 2 plus 5 plus 4. It's 11 days. Therefore, the critical path is ADE because it's longer. There are some basic rules governing the development of project networks. First of all, project networks typically flow from left to right. By convention, most project management software follows this rule when a project network is displayed on the computer screen. Second, the activities will be performed in sequence. An activity cannot begin until all predecessors are complete. In the diagram at the top, B can start only after A is finished. In the diagram at the bottom, Y and Z cannot start before X is finished. Third, each activity must have a unique identification code. It could be a number or a letter. An activity's identification code must be greater than that of any predecessor activities. A is followed by B, and B is followed by C. X is followed by Y and Z. Network numbering is frequently not done until after the network is complete. The fourth rule is that arrows indicate precedence and flow, and they can cross over each other, like the one at the top. The fifth rule is that conditional statements are not permitted in a project network. One example of the conditional statements is, if test is successful, then build the prototype, otherwise redesign. Also, looping is not allowed in a project network. In the diagram at the bottom, this is an example of looping. It attempts to return to an early activity from Z to X. If this loop were allowed, this path would perpetually repeat itself and the project may never end. Many computer programs catch this type of logic error. The last rule is that if there are multiple starting nodes in a project network, they should all be tied together to form a common project start. Similarly, if there are multiple end nodes, they should all be tied together to form a common end. We use a pseudo or dummy activity as a common start node and a common end node. In this example, we originally have two starts, B and C. We introduce a dummy node A as a common start, so the project has only a single starting node. In this second example, we originally have three ends, J, K, and L. We introduce a dummy node M as a common end, so the project has only a single end node. Now let's see how we can develop a complete project network for a smartwatch project based on information in this table. This table contains 8 activities, from A to H. The first step is to identify the project start. Activity A, define requirements, has no predecessor, so it's the starting node of the project network. A is a predecessor of activity B, design software, and C, design hardware. So we draw 2 arrows from A to B and from A to C. B is a predecessor of D, code software. We draw an arrow from B to D. Activity C is a predecessor of E and F. So we draw 2 arrows, C to E and C to F. D is a predecessor of G. Let's draw an arrow from D to G. Lastly, E, F, and G are all predecessors of activity H. So we draw 3 arrows, G to H, E to H, and F to H. And now the network is complete. Note that in this diagram, there is no time information. This is because the duration of the activities are not provided in the table. Now let's assume the project manager used the bottom-up method to estimate the time for each activity. Such time estimates are extracted from the work breakdown structure, and they are listed at the last column in this table. Activity A takes 20 workdays, B 10 workdays, etc. Then we can update the project network and add the duration of each activity. Each activity is represented by a 9-cell block. The bottom right corner shows the meaning of each cell in the block. This new format will be used throughout this project management course. ID in the top center cell is the identification code for each activity, like A and B in this network. The middle center cell shows the description of an activity, like define requirements or design software. DUR in the bottom center cell is the duration of the activity, like 20 workdays, 10 workdays, etc. The other 6 cells, ES, EF, TS, FS, LS, and LF, contain important time and slack information for each activity. We will fill out these blanks for each activity block. ES in the activity block means early start. It's the earliest time the activity can start. EF means early finish. It's the earliest time the activity can finish. We will use a method called forward pass to calculate these earliest times. Forward pass begins with the project start time, which is usually time 0 for the first node. Then we add activity times along each path in the network. The early finish time EF of an activity is equal to the early start time ES plus its duration. After that, we carry the early finish time EF to the successor activity, where it becomes its early start ES. However, if the successor is a merge activity, the largest early finish time, EF, of all its immediate predecessor activities should be carried to the merge activity at the early start, ES. This process is repeated along each path of the network until all the activities have been covered. This method may seem complex. Let's see an example to understand how it really works. I'll just put this equation at the bottom left corner for reference. Activity A starts at time 0. So its early start equals 0. Its duration is 20 workdays. So early finish is 0 plus the duration 20, and it equals 20. A has 2 immediate successors, B and C. Neither of them is a merge activity. So we carry the early finish 20 to activities B and C at the early start time. B has a duration of 10 workdays. So its early finish is 20 plus 10, and it equals 30. For activity C, 20 plus 50 equals 70. For D, the early start time will be 30. Early finish is 30 plus 40 equals 70. Carry this over to G. 70 plus 70 is 140. Because the successor H is a merge activity, we have to wait and calculate the early finish time for E and F first. We carry 70 to E and F. 70 plus 100 is 170. 70 plus 30 is 100. Activity H has 3 immediate predecessors, G, E, and F. Out of these 3 predecessors, activity E has the largest early finish time. So we carry 170 over to H. 170 plus 30 is 200. Because H is the end node of the project network, we conclude that the earliest finish time of the whole project is 200 workdays. LS in the activity block means late start. It's the latest time the activity must start. LF means late finish. It's the latest time the activity must finish. We will use a method called backward pass to calculate these latest times. Backward pass begins by setting the late finish time LF of the last activity to its own early finish time, EF. The late start time LS is equal to the late finish time LF minus the duration of that activity. Then we carry the late start LS to the next predecessor when it becomes its late finish, LF. However, if the predecessor is a burst activity, we must choose the smallest late start LS value of all its immediate successor activities. Again, let's explain the backward pass process using this example. We already know from forward pass that the early finish time EF of activity H is 200. We start by setting late finish LS of activity H to 200. So late start equals late finish LF minus the duration, that is 200 minus 30. The result is 170. None of its predecessors is a burst activity. So we carry the late start 170 to activities G, H, and F as the late finish. For G, the late start is equal to 170 minus 70, which is equal to 100. We carry late start of G to D and repeat the process. 100 minus 40 equals 60. Similarly, 60 minus 10 equals 50. Because A is a burst activity, we should wait here and do the calculation for other branches. For E, 170 minus 100 equals 70. For F, 170 minus 30 equals 140. C is a burst activity. Its late finish is equal to the smaller of these two values, which is 70. For C, 70 minus 50 equals 20. Activity A is a burst activity. The late finish should be the smaller of these two values, which is 20. The late start of activity A is 20 minus 20, we get 0. After we get the earliest and latest times of each activity, we can use them to calculate the total slack. Total slack is also called total float. It tells us the amount of time an activity can be delayed without delaying the entire project. It's how long an activity can exceed its early finish time without affecting the project end time. Mathematically, the total slack is the difference between the late start and early start. It's also the difference between the late finish and the early finish. Let's just apply the equation shown at the bottom left corner to all the activities. For A, late finish minus early finish is 20 minus 20. The result is 0. Or late start minus early start, 0 minus 0, it's still 0. So the total slack is 0. That means any delay in activity A will cause delay of the entire project. For B, total slack is 60 minus 30, or 50 minus 20. The result is 30. It means the early start, which is day 20, can be delayed by 30 days to day 50 without delaying the whole project. Any more delay beyond 30 days for activity B will delay the project. For D and G, they are also 30. For C, E, and H, there is 0 total slack. For F, the total slack is 70. Another type of slack is called free slack or free float. It's the amount of time an activity can be delayed without delaying any immediate successors. It measures how long an activity can exceed its early finish time without affecting early start times of any successors. Mathematically, the free slack of an activity is the difference between the early start of its successor and its own early finish. Only predecessors of a merge activity can have free slack. Other activities will not have any free slack. The smartwatch development project network has only one merge activity, which is H. So only G, E, and F may have free slack. Therefore, we write free slack equals 0 for all other activities. We apply the equation shown at the bottom left corner to activity G. The early start of its successor H is 170. The early finish of itself is 140. So the free slack of G is 170 minus 140 equals 30. Then apply this equation to E. The early start of its successor H is still 170. The early finish of itself is 170. So the free slack of E is 170 minus 170 equals 0. Finally, let's apply this equation to activity F. The early start of its successor H is 170. The early finish of itself is 100. So the free slack of F is 170 minus 100 equals 70. Therefore, activity G and F can be delayed by 30 and 70 days respectively, without delaying their successor activity H. Other activities cannot be delayed without affecting their successors. After we are done with the computation and get the complete project network, we can start to identify the critical path. The critical path is the longest path through the activity network. It measures the shortest possible time in which the whole project can be completed. It's also the path that has the least slack. In this example, we have a total of 3 paths from A to H. They are ABDGH, ACEH, and ACFH. For the first path, the length is the sum of their durations, 20 plus 10 plus 40 plus 70 plus 30 equals 170 days. The length of the second path is 200, and the third path is 130. Therefore, ACEH is the longest and is the critical path. It's marked with blue dashed arrows. The project will need 200 workdays to finish. Since the critical path determines the project completion time, the project manager should put best people on these critical activities and pay extra attention when doing risk assessment. Critical activities typically represent about 10% of all the activities of the project. The project manager should closely monitor these critical activities when they don't have time to monitor all activities. These activities are the ones you won't even consider when other managers ask you to borrow people or equipment. Network sensitivity measures the likelihood the original critical path will change once the project is initiated. A project is insensitive if it has only one critical path and the non-critical activities enjoy significant slack. A network is sensitive if it already has multiple critical paths and non-critical activities have little slack. So in a sense, sensitive projects are fragile and more prone to delays. Let's check how sensitive this project network is. There is only one critical path in the network. It's ACEH. In the non-critical path, ABDGH, there are 30 days of total slack. In the non-critical path, ACFH, there are 70 days of total slack. Therefore, this network is insensitive. All of the tools and techniques discussed in this video can be implemented with computer software like Microsoft Project. Microsoft Project will do the calculation automatically and show you the final results and the network after you typed in the start date, the time unit, and the duration of each activity, as well as non-work days and sequencing of the activities, etc. For example, This screenshot shows the schedule table on the left with information such as ID of each activity, duration, task name, early start date, early finish date, late start date, late finish date, free slack, and total slack. On the right side, it also shows the automatically generated Gantt chart for the project. In the Gantt chart, the blue bars represent the activity durations. The extended lines from the bars represent slack. This screenshot shows the automatically generated project network. The critical activities and critical paths are highlighted in pink. Let's zoom in the top left corner to see the details. Each block contains information such as activity name, ID, early start and early finish dates, and duration. When we build the smartwatch project network, we assume that all predecessors must be 100% complete before the next activity can begin. This relationship is called the finish-to-start relationship. In real-world applications, this assumption is too restrictive for some situations involving activities with long durations. Instead of waiting for the entire activity to be 100% complete, we may break it into multiple segments and start the next activity after a segment of the predecessor is complete. This is called the laddering approach. It can finish the entire project sooner. An example of the laddering project is building a road. Huge earth-moving machines must be used to create a solid foundation. Then bulldozers and graders move around dirt delivered by dump trucks to create a level surface. Finally, gravel is added in layers and machines roll over the surface to compact and flatten it further. We can split the 1-mile road into 3 segments. After the foundation is done for the first 30 miles, we may start the surface work while preparing the foundation for the next 30 miles. After the surface of the first 30 miles is done, we may immediately start to add gravel. Therefore, the laddering process will finish the project much faster. A project network may involve relationships between activities other than finish to start. We summarize these relationships using a term called lags. The use of lags has been developed to offer greater flexibility in network construction. A lag is the minimum amount of time a dependent activity must be delayed to begin or end. Lags can be used to constrain finish to start, start to start, finish to finish, start finish, or combination relationships. The finish to start lag is used in situations where the next activity in sequence must be delayed even when the predecessor is already complete. For example, removing concrete forms cannot begin until the poured cement has cured for 1 day or 24 hours. Or, it may take 1 day to place the order, but take 3 days to receive the goods. The start-to-start relationship with a lag of 5 time units is shown here. The time units could be hours, days, weeks, or months. Activity B cannot begin until 5 time units after activity A begins. The start-to-start lag can be used in laddering projects so activities can work concurrently, and the projects can be finished more quickly. This is a finish-to-finish relationship. The finish of activity B depends on the finish of activity A. For example, in a mobile app development project, software testing cannot be completed any earlier than 3 days after the prototype is complete. This is a start-to-finish relationship. The finish of activity B depends on the start of activity A. It shows that system documentation cannot end until 5 days after testing has started. This is probably because all the relevant information to complete the system documentation is produced after the first 5 days of testing. Lags can also be used to represent a combination of relationships. This example shows a start-to-start and finish-to-finish combination tied to two activities. Debugging cannot begin until 3 weeks after coding has started. Coding must be finished 5 weeks before debugging can be finished. This diagram shows a project network with a lot of legs. We can read this network this way. 2 days into the design of the system, which is activity A, it is possible to order the required hardware, which is activity B. It takes 3 days after the order is placed for the hardware to arrive, so it can begin to install software, which is activity C. After 2 days of installing the software system, the testing of the system can begin, which is activity D. System testing, activity D, can be completed 4 days after the software installation is complete. Preparing system documentation, activity E, can begin once the design is completed, activity A. But it cannot be completed until 3 days after the system is tested, activity D. The forward pass and backward pass can still be used to calculate the information such as early start, early finish, late start, late finish, total slack, and free slack. Just remember to account for the lags when doing these calculations. This task is left for you to practice. Finally, the critical path is A, B, C, D, E. The duration of the project, including lags, is 34 days. To sum up, in this video, we talked about how to create a project network using the activity on node method. We learned how to calculate early times, late times, slacks, and how to identify the critical path. We also discussed how to use lags to constrain project activities. This is Wang, and I'll see you in the next video.